I have been working through this physics problem of a tipping over stick. So imagine that I have, you can't really see it, but imagine I have this pin right here and it tips over and falls like that. And I want to model that. And I've already done it twice. And I'm going to do it at least 2 more times because, I do this. And yes, I have other things I need to do, but I want to do this. So a couple of simplifications here. First of all, I'm not going to use a stick. Okay. Instead, I'm going to use two masses connected by zero mass stick. And that just makes things a little bit easier to model, both in Python and the way I'm going to do it today. 2, I've already done this twice. So the first way I did it was to say, okay, suppose I have this pivot point down here fixed, and I'll let this tilt over with, again, a single mass, and there's a mass stick right there. So the first way I did that was to essentially do this I use torque and angular momentum, and to calculate the angular acceleration, and then use that to find the updated theta position, and then just move everything. The second way I did it was to say that the stick was actually a spring, and then I just use forces. So I calculate the force from the spring on that, and the gravitational force, and let it go down. I like this way better. I mean, this way models better, but this way I think people understand conceptually. There's a couple tricks with this one, but that's fine. But both of these cases, the pivot point was fixed, and now I want to see what happens when the pivot point moves. And so to do that, I can't do just normal angular momentum because it's not just rotating. And you could do some tricks to figure that out. It's actually not too bad, but I want to use this as an example to do a Lagrangian solution. So if you haven't done Lagrangian mechanics and you don't want to do Lagrangian mechanics, then just don't watch this video. Okay. But if you want, I think it's a great example for Lagrangian mechanics. So I'm going to go ahead and do that. The idea of Lagrangian mechanics, and I'll have a video, an introductory video, I'll post it down below. The idea is that we can define a system in terms of some generalized coordinates. And with those generalized coordinates, we can calculate the kinetic energy T and the potential energy U, and define the Lagrangian as T minus U. And then it turns out the equations of motion are those that for which the action is minimized, which is a path integral in space. I know I don't want to get into it. But the end of that, we have this Euler-Lagrange equation, which says that there is my Lagrangian, Qi, those are my generalized coordinates. They could be x and y, but they could be theta, they could be anything. So the partial of that with respect to q minus the derivative of L with respect to Qi dot, where Qi dot is the time derivative of that. Just in general. Okay, so here's my stick. I need to I actually have 2 generalized coordinates here. And you can pick whatever you want, but I think if you imagine this thing is sliding, then let's just draw this at some other position. And what 2 coordinates could I use to describe this? Well, the first would be this value of x, which is the location of the bottom mass on the x-axis. And then the other is this angle theta. But you'll notice that I can't just use theta to describe the motion of this. It depends on the position of x also. And let me say, sometimes I would work out these problems beforehand, but I didn't, so I might make some mistakes, and that's what just makes everything so much fun. Okay. So I need to write the kinetic energy term and the potential energy term. Now, I can't just write kinetic. I probably could, but I'm not just going to write the kinetic energy term in terms of theta because it's not so easy, right? So instead, what I want to do is to describe this in Cartesian coordinates in relationship to these generalized coordinates. So I'm using x, and let's say the position of this is going to be x1, y1. So now I can write the kinetic energy. T equals 1/2 m x dot squared, and again, that's the time derivative of this coordinate with respect to with time squared, plus 1/2 m x1 dot squared plus y1 dot squared. Right. So if I know the Cartesian coordinates, I can write the kinetic energy fairly easily. Now I just need to get these Cartesian coordinates in terms of my variables x and theta. So if I know the location of this mass, I can find x1. I can say x1 is going to be x plus this length, right? And that's the angle theta, plus L sine theta, right? Because if this is the location of the mass, which that is a Cartesian coordinate, and I just go over a length L sine theta, depending on that angle theta, then I get to x1. And the same thing's true, y1 is going to be equal to just L cosine theta, because y is 0 down here. It doesn't move up and down. Now, if I have this, I can take the derivative of x1, and I'll get derivatives of x and theta, and that's what I want. Okay, so let's do that. So x1 dot is going to be the derivative with respect to time of x, which is x dot, plus the derivative of this with respect to time. So now I have to take the derivative of L sine theta. That's going to be plus L cosine theta. But then I have to take the derivative of the inside theta, so I get a theta dot. Same thing down here, y1 dot. It's going to be the derivative of cosine theta is negative sine, so I get negative L theta dot sine theta. So don't forget to take the derivative of theta, right? It's not a partial derivative, it's a derivative. So you gotta do everything. So now I have x1 dot, y1 dot. To plug them in here, I just need to square these. So let's write that out. Let me move this up a little bit. So x1 dot squared, and I'm going to write out the whole thing, plus y1 dot squared. Okay, so this one I'm going to get x dot squared, and then I'm going to get two cross terms, plus 2L theta dot x dot cosine theta, and then I'm going to get this squared, that squared, plus L squared theta dot squared cosine squared theta. And then I have to square this one, and that's easy, plus L squared theta dot squared sine squared theta. Now you'll notice right here that I can factor out the L squared theta dot squared, and I'll get cosine squared theta plus sine squared theta, which is 1. So that means this is going to become x dot squared plus 2L theta dot x dot cosine theta plus L squared theta dot squared. And that's my term right there. Okay, what about the potential energy? Well, the potential energy is just going to be U is mgy1, and so that's just going to be equal to mgl cosine theta. So we can write down the Lagrangian and then start taking derivatives. Okay, so let me write my Lagrangian. I have my paper right there. Okay, so L equals 1/2 m x dot squared plus 1/2 m. Now I'm going to put in my expression for x1 dot squared plus y1 dot squared, which is x dot squared plus 2L theta dot x dot cosine theta plus L squared theta dot squared. And then I have to subtract the potential energy. So I'm going to say minus mgl cosine theta. Okay, so I get some simplification here because look, I have a 1/2 m x dot, 1/2 m x dot. So let's just write that as, let's take those two and multiply them. This only works if the two masses are the same, which I have in this case, but I should do a general solution, but I'm not going to. So let's go m x dot squared plus, then I'm going to get 1/2 m multiplied by the 2, so I get plus m L theta dot x dot cosine theta, and then I have this plus 1/2 m L squared theta dot squared minus mgl cosine theta. Okay, so the first thing I'm going to do is to take the partial of L. I have two variables. Let's just do x first. Partial of L with respect to x, right? Because I need to do the partial of L with respect to x, that's one of my variables, and then the partial of L with respect to x dot, then take the derivative. And then those two things should be equal to each other. So the partial of L with respect to x. Now this is a partial derivative, so it's a little bit easier. So here's my L. I'm looking for anything with x in there. That's x dot. No, 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 no. There is no x, so that's 0. Now I can take the partial of L with respect to x dot. Okay, here's one. I get 2m x dot, and that's a partial. And then here's another one. I get plus m L theta dot cosine theta, and that's it. Those are my only x dots. Now I can take the derivative of that with respect to time, and yeah, it is equal. I could just say this is equal to a constant, but I'm not going to. So I'm going to take the derivative of that with respect to time, partial of L with respect to x dot. Okay, so here I get m doesn't change, but x does. So the derivative of x dot with respect to time is x double dot. 2m x double dot. And then here I have two terms that depend on time, theta dot and cosine theta. So the first, I'm going to get two terms. So I'm going to get plus m L theta double dot cosine theta plus, that's going to be minus. Going to take the derivative of cosine theta is negative sign. So I can get minus, can I fit it in here? Minus m L theta dot. And then I'm going to get another theta dot in there, squared sine theta. And that is equal to 0. So that's one of my equations. It's an important equation. And let me go ahead and let you know what I'm going to do. I need to solve this equation for x double dot. Okay, actually I could solve. Actually now I'm thinking I got a theta double dot in there too. I think this might work. I'm just going to solve this for x double dot. So x double dot equals, if I move this stuff to the other side, divide by 2m, I get L theta dot squared sine theta over 2. So 1/2, right? Because I divide by 2m. And then minus 1/2 L theta double dot cosine theta. Okay, I might have to simplify that when I get to the theta term. Okay, now let's do the theta term. So I need to do the same thing. I need to take the partial of L with respect to theta, the partial of L with respect to theta dot, and then take the derivative of that with respect to time. I feel like I'm making this, I feel like I'm making a mistake somewhere, but you know what? You can make mistakes. You just gotta, you won't know until you get to the end. Okay, and there are ways we can check and see if our solution is legit or illegit or too legit to quit. That was a bad joke. I'm sorry. Okay, so let me write down the Lagrangian. L equals 1/2 m x dot squared plus 1/2 m x. Oh, I wrote it down here. L equals m x dot squared plus m L theta dot x dot cosine theta plus 1/2 m L squared theta dot squared minus mg L cosine theta. And I want to take the partial of L with respect to theta. Okay, so I'm looking for terms that have theta in it, no theta. Here's the theta, and I'm taking a partial. So the partial of cosine theta with respect to theta is negative sine theta. So I don't have to worry about taking the derivative of the theta. It's a partial. So I get minus m L theta dot x dot sine theta, no theta there, here's another theta, and I get plus m g L sine theta. Now let's just double check, because all these should have the same units. So this is, they both have mass. This is theta dot is radians per second times meters per second. So this is meters per second squared. And that's meters per second squared, and then I have the L. So they do have the same units. Okay, now let's take the partial of L with respect to theta dot. Okay, so I'm looking for theta dots. There's one, and that's pretty easy. So I get mL x dot cosine theta. Here's the theta dot. I get plus mL squared theta dot, right? Because I pull it's a power of 2, so I bring the 2 down, and then that's just theta dot, and that's it. Now I can take the derivative of this with respect to time, and I'll do it right here. the derivative with respect to time of the partial of L with respect to theta dot. Okay, so right here, now is this an actual derivative? So look, I have an x dot and a cosine theta. Both those have to take a derivative. So let's do this first, the x one first. So I get m L x double dot cosine theta. Now after this term, I get minus m L x dot. I'm going to get a theta dot when I take the derivative of the inside. I want to put it right there. Theta dot sine theta. So that's the derivative of that term. Now over here, I only have one term that depends on theta or time, and it's theta dot. So I get plus m L squared theta double dot. Now I can set this equal to that. So I have m L x double dot cosine theta minus m L x dot theta dot sine theta plus m L squared theta double dot. And then that's going to be equal to that negative m L theta dot x dot sine theta plus mg L sine theta. Again, I have x double dot. I'm really looking for the second derivative terms. I need the second derivatives. So here I have an x double dot. I have a theta double dot. And so I have a whole bunch of other stuff. And let's write down my other equation that I had before. X double dot equals 1/2 L theta dot sine theta minus 1/2 L theta double dot cosine theta. That's what I had before. Okay, so I have that. I could plug that in over here and then solve for theta double dot, and that's what I want to do. And so I have two equations, two unknowns, and it looks messy. Okay, so let's just let's see if there's anything that combines together. Here I have a m L x dot. Oh, here's one. So that cancels. That's kind of cool. Okay. So it's not so bad. Let's go ahead and just plug this in over here. And then solve for theta double dot. Okay. So I get, the masses cancel. The L's cancel. Some of them. Yeah. Okay. So now I'm going to plug in x double dot into my thing. So I get, this is just x double dot times cosine theta. So I put that up here. I get 1/2 L theta dot sine theta cosine theta minus 1/2 L theta double dot cosine squared theta. So that is that term right there. Putting that in. That term went away. Then I have plus L theta double dot. And then I have equals G sine theta. So I have two terms with a theta double dot. That's what I want. Let's subtract this from both sides and then factor out the theta double dot. So I get theta double dot times negative 1/2 L cosine squared theta plus L equals G sine theta minus 1/2. If this works, what? Okay. Minus 1/2 L theta dot sine theta cosine theta. So then I can solve for theta double dot by dividing this. I'm going to do that. I'm going to write it up here. Theta double dot equals G sine theta minus 1/2 L theta dot sine theta cosine theta. All of that over negative 1/2 L cosine squared theta plus L. Okay. So I think if I didn't make plus L. Yeah, okay. If I didn't make a mistake, then this is going to work. Because right here I have theta double dot in terms of theta dot theta. And here I have x double dot in terms of theta dot and theta dot. And I can use this to model the whole thing. And I'm going to use the Euler method to do that. So here's what I'm going to do. And I did this before. I'm going to break this motion into short time intervals. During those time intervals, I can assume theta double dot's constant and x double dot's constant. And I can use that to find the new x dot and the new theta dot. So let's look at theta dot first. So let's say theta double dot is equal to delta theta dot over delta t. And so I'm assuming theta double dot's constant if my delta t is small, which it's not true, but it's kind of true, so it's okay. And so this is going to be theta 2 dot minus theta 1 dot over delta t. So I can solve that for theta 2 dot, and I get theta 2 dot equals theta 1 dot plus theta double dot delta t. So if I know the initial theta dot, the initial angular velocity, which I'll set to 0 if I release it from rest, and I know I can calculate theta double dot, right? I just calculated that as an equation, and I know my delta t of, let's say, 0.001 seconds. Then I can calculate theta 2 at the end of the time interval. I can do the same thing for theta dot. I can assume that that's constant, which it's not. So it's delta theta over delta t. So I get is equal to theta 2 minus theta 1 over delta t. So theta 2 equals theta 1 plus theta 2 dot delta t. And so here, if I just calculate, the question is, what theta dot do I use? I'm going to use the theta dot I got at the end of that calculation. You could use something else, but this one works fairly well. And so that's that. And then I can update time. I can also do the same thing for x double dot and x dot, and I get x2 dot equals x1 dot plus x double dot delta t. x2 equals x1 plus x2 dot delta t. So I can calculate x double dot because I just wrote that as an equation. Then once I have x2 and theta 2, I can move all my stuff in Python and animate it. Okay, and then we can check and see if things work. So let's do that. I mean, I could stop here, but why stop now? Never stop. Never surrender. Okay, so this is the equation that I need right there. These are my two equations. So let's go and go to Python. So here we are in Python. This is my old program, right? Let me run it for you. So this says I use the angular acceleration on the same idea, but the pivot point did not move. And then I have this other ball, which I'm going to delete. Okay, so that works. Okay, so let's go ahead and clean some stuff up here. So I'm going to get rid of ball 2. And then I'm going to leave all that stuff. Anything with ball 2, I'm going to get rid of. I'm going to get rid of all that stuff. Okay. Now let's go ahead and fix the pivot point. I should call that something else. I should call it ball 2. I want the same radius as my ball, which is 0.05. I'll leave it the color. Should I change the name? I probably should. Let's call it ball 2. I'm going to make a mistake here. Ball 2. Okay, so down here, this is going to be ball 2, ball 2. I think I can do this. Down here, I'm going to leave it the same way, just make sure everything's working. Ball 2, ball 2. Okay, let's see if it runs. It didn't. Can't find pivot. I missed a pivot. Oh, here's one. You shouldn't change names. Okay. Great. That's working. So now what I want to do is to calculate my two things down here. So I'm going to start in the same position. So the first thing I'm going to do is to calculate theta double dot, right? I can't calculate x double dot until I calculate theta double dot. I do need a value for x and x dot. So let's say x equals 0, x dot equals 0. So down here, I'm just going to type in my equation for theta double dot, which I have theta d dot right there. I just need to change this. So I'm going to put in my new equation for theta double dot, and it is g times sine theta. And I already have an initial theta. I already have initial theta dot. Sine theta, g sine theta, minus 0.5 times L, which I do have an L, don't I? Yep. Times theta dot, which I have. It starts at 0. Times sine theta times cosine theta. Sine theta times cosine theta. And this might be wrong. If it is, then we're just going to deal with it. All of that divided by negative 0.5 times L times cosine theta squared plus L. Okay, so that's my theta double dot. Now once I have theta double dot, I can calculate x double dot. So x dd dot is going to be equal to 0.5 times L times, I'm looking at my notes over here, theta dot minus 0.5 times L times theta double dot, which I just calculated. Theta d dot times cosine theta. So now I have x double dot, I have theta double dot. This next equation, I guess I should make this a little bigger. This next equation is the same, right? It doesn't change. I'm still updating theta double dot. I'm still updating theta. But I need to update x and x dot and x double dot. So x dot equals x dot plus x double dot times dt. And then x equals x plus x dot times dt. And I did already update time. Okay, so now I need to update. I'm going to move ball 2 first. So ball 2.pos equals vector x0, 0. No, actually, ball 2, it was at this. It had a y value of negative 4.5. 0.45. Negative 0.45. Okay, so but I calculated the next value and I moved it. Now, ball 2 is going to be dependent on ball 1, and I just moved ball 1, right? So I don't actually even need to change that. And the stick, too. I think this should work. Okay, and then there is something I can do to test and see if it works, because I know something. If this works, I'm going to give myself a double high five. I'll deserve it. And I'm not 100% sure that it's going to work. I do believe in myself, but I'm also realistic. Okay, actually that worked. I did make one error, and that was my stick. I'm gonna go ahead and give it that's a double high five for me right there. That worked. What I did here was I moved the axis, but I didn't move the position of the stick. So I'm gonna say stick. In the previous case, it didn't move. Stick.pos equals ball2.pos. That's all I need to do. Okay, let's run that again. I didn't save it. Did I even copy this? Oh, I didn't. Oh, I'm a bad person. Let's copy all this and open a new trinket. I meant to copy it. Let's see. So I'll go to new trinket and paste this in here, run it, and I'll put close script in there twice. Okay, and now I can save it. Slipping, tipping over stick. I kind of like the name of that. Okay, so now how do we know that it's legitimate? What can I do to say this is legitimate code? Well, one thing is that if you think about the center of mass, I'm not going to make a plot on this because I've already gone 30 minutes. I like to keep 30-minute videos. If you think about a plot of the center of mass of this, the center of mass is right there. And the center of mass should not move in the x direction because there are no x forces in the x direction, so the center mass can't change. And that's the way it should be. Now, if I had been smarter, I would have made this a independent masses, and I could make that mass very, very large. And then you could see that if the mass of the bottom ball is very, very large, you should get back to the pivot location. I really should have done that, and I apologize. But that can be a homework problem for you. So I think I'm done. I am going to do this again. I'm going to do this by modeling it with springs like I did before. The math is a little bit easier. It doesn't run quite as nice, but it's still a great way to do it. And the nice thing with the spring thing, I'm going to tell you where I'm going, is if I have the springs, I can add friction in with that pivot point. Whereas in the Lagrangian, you can't really easily add friction. It just doesn't work very well with that. So this code's down below. The link to my other 2 videos down below. A link to my Lagrangian video is down below. And if you have any questions, just let me know.